In this conceptual aside, we'll talk about something you need to understand if you're going to deal with server code in Node. But if you're coming from web development primarily in the browser, you may not have dealt with as much. We're going to talk about binary data, character sets, and encoding. Big word alert. What do we mean by binary data? Well, that's data stored in binary, which is sets of zeros and ones. And you probably are familiar with the idea that a computer is essentially representing data in zeros and ones. It's the core of the math that computers are based on. Each one, or zero, is called a bit, which is short for a binary digit. And when we're talking about binary data, we're really talking about numbers. A binary number like this one is representing a value with only two digits, either a 0 or a 1. How does it do that? Well, it's math. Looking from right to left, each digit is associated with 2 to the something power. So 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third is 8. And so then we multiply these values. Now 0 times anything is 0, so we end up with 1 plus 0 plus 4 plus 0. See that? 1 times 2 to the second is 4. 1 times 2 to the 0, 2 to the 0 is 1, and then we add them, and so this is the binary representation of 5. This is the number 5 in binary. And because each place we're calculating based on 2 to the something power, we call it base 2. That's binary. It's base 2 representation of a number, and we only need then 2 digits to represent this number. It actually works the same when you're dealing with numbers that we're used to, like 53. Well, how do we know this is 53? Well, there's a 3 and there's a 5. And going right to left, 10 to the 0 power is 1, and 10 to the first power is 10. So we multiply, and then add the result. So it's 50 and 3. So that's right, that's why it's 53. This is the math that we're used to doing, and because we're basing it off 10 to the something power, it's base 10. And we need 10 digits to represent it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Those are the 10 digits that we use to represent numbers. But binary only needs 2 digits to represent numbers, a 0 and a 1. And for that reason, binary is awesome for computers, because we can easily represent binary data physically. For example, inside a Blu-ray or a DVD, we're representing binary data with bumps. As you move the CD or Blu-ray as it's spinning, lasers are hitting the Blu-ray and bouncing back. And as they transition from a bump which is slightly elevated to not having a bump which is lower and vice versa, it registers that as zeros and ones. So depending on where the bumps are placed, on either side of the bump can represent a 1, and then when not in a bump can represent a 0. So you have a way physically to represent zeros and ones. Inside your computer, there are transistors, essentially whether electricity is flowing or not, switches, like this light switch in your house. Imagine every light switch being on being 1 and off being 0. I can represent a number with switches, and there are a lot of switches inside your computer. And the same is true with your hard drive and with flash drives and everything else. They're just different ways of physically representing an on or off state, a 0 or a 1. And because of that, we can physically store numbers, and that lets us store data. And that actually takes us to the idea of character sets and character encodings, because everything we store is in binary, which means everything we store is really numeric. We're storing numbers. And that means in order to store other kinds of data, we have to represent everything we store as a number. So, big word alert, a character set, a representation of characters as numbers, kind of like a code. And it is a code, really. Each character gets a number. Unicode, ASCII, those are types of character sets where characters get a number assigned to them. Like hello. I can give each letter in the alphabet and every other character I might type a number that represents it. And what number I decide to give it, what number each character gets, defines a particular character set. In this case, we're showing you what each letter gets in the Unicode character set. But there are other character sets. And all it is me saying, hey, I'm going to decide on a number that means a particular letter. So I can map a number to a letter. That's a character set. Now, Unicode is very popular because while we may have a small amount of characters in languages like English and Spanish and French and others, there are other languages that require a lot more characters, like Japanese or Chinese or others. And so we need larger character sets, and for that reason, we need bigger numbers, because we need more numbers available to us to be able to represent all the characters. And that means we need more bits for every character. So in this case, we're just saying that we're going from the letter to a number. But remember, the number itself is stored in binary. So big word alert. Character encoding. How characters are stored in binary. So those numbers from the character set, those are called code points. And they're converted and stored in binary. Now, there are different ways that I could store a number in binary. And so I have a number, and the character set says, all right, here are the numbers that each one represents. And then the character encoding, in this case we're showing UTF-8, determines how we're actually going to store the number in binary. Now, you might be thinking, but there's only one way to store a number in binary. Each number is specific zeros and ones, and that's true. But when we're talking about encoding, what we're really talking about fundamentally is how many bits we use to represent each number. In this case, UTF-8, we have 8 bits, 8 digits to represent a number. You can see that each number gets 8 bits available to it, even if it doesn't need all of them, even if there's zeros to the far left. And the reason is because the more bits, the more digits we have, the bigger the number we can represent. So UTF-8 is popular because the more numbers we have, the more characters we can use, and so it's great for international usage, for languages that have more characters than others. And all these zeros and ones don't have the spaces like they do here, but rather are just crammed together as a sequence of data. And so we know that every 8 digits, we're getting another piece of data. And since it's character encoded UTF-8, we know it's 8 bits. And so we can figure out what the number is. And that number is a character set. And so in this case, Unicode, the number matches to a letter. And so we know what letter that binary number represents. Make sense? So character sets and character encodings. When we talk about character sets, we're talking about what number is each character represented by. We assign each character, letters and symbols, a number. Character encoding means how many bits are we using to store that number. The more bits, the more characters we can store because the number is bigger. UTF-8 on the internet is by far the most popular. And when dealing with a server, you need to be able to deal with binary data, character sets, and character encodings, and historically, JavaScript is not very good at the encoding part. JavaScript handles Unicode okay, translating letters to numbers and back and forth. But the pure raw binary data, JavaScript doesn't have a lot of features to deal with. And so because of that, Node, with V8, the engine embedded in it, expands on the JavaScript language and gives us some mechanisms to deal with binary data, raw zeros and ones. This is good because if we're dealing with files or information flowing across the internet, in JavaScript, we need to be able to deal with binary data. All right, so character sets, numbers to letters, character encoding, numbers in base 10 to numbers in base 2, to binary, and how many bits we're using, how many digits we're using to store that. Got that? All right, we're ready to move on.